Hello, and welcome to your first set of Chemistry 2 video notes. The videos for this class will serve as a summary of the most important information from each chapter. You are highly encouraged and sometimes required to dig a little deeper and read the chapter as well. In today's video, we're going to talk about some of the most basic concepts of chemistry and science in general. We'll talk about science and technology, matter, physical and chemical transformations of matter, the scientific method, and how to get the most out of your textbook. In the last 100 years, technology has evolved at an exponential rate. Just think of what life was like 100 years ago. Our main method of communication was the telegram. Now we have cell phones that can communicate instantly across the world, and they fit in our pockets. We knew about DNA, but we had no idea that it was linked to genetics. Now we've mapped the whole human genome and can even clone DNA. Technology's been evolving so rapidly that we've been using it to define generations. Up until recently, each generation lived pretty much the same life as the previous one, with a few minor upgrades. Now, someone born in 1985 has lived a completely different life than someone born in 1995, and even a more different life than someone born in 2005. Scientific advancement is the driving factor behind all of this rapid change. Science is defined as the experimental investigation and explanation of natural phenomena. In other words, it's the knowledge we gain from experiencing or observing a natural phenomenon. Science is driven by curiosity and is done solely for the sake of knowledge. What people do with that knowledge is called technology. Technology is simply the application of science. The more we learn through science, the better technology we can create. You might ask, well, is science always correct? The whole nature of science is finding new information that contradicts old information so we can come up with a better explanation. You've probably seen headlines in the news claiming something like, how coffee is good for you. But then a year later, you see another headline claiming that coffee is actually not good for you. A lot of those headlines you see in the news aren't based on good science. Science is carried out by humans, so it naturally comes with a margin of error. Some scientists may have a big ego, might make mistakes, or just be really stubborn, which can lead to bad science and does get in the way of finding the truth. In a perfect world, science is solely driven by curiosity, and technology uses that information to advance the world. In the real world, it often goes in the opposite direction. Companies are driven by profit, governments are driven by a need to be stronger than their enemies, and sometimes just entities are driven by the desire to better humankind. Science is often driven by one of those factors instead of solely by curiosity. My point is this: when you hear a news story or read an article about some type of scientific advancement, look for the motive, judge the process, and determine for yourself whether that scientific advancement should be deemed good or bad. In the scientific community, the results from new research are heavily scrutinized by other experts in the same field and are only accepted as scientific fact after they make it through that rigorous peer review process. This year, as you learn chemistry, the two key factors we'll focus on are matter and its transformations. So what is matter? Matter is anything that has mass and occupies space. There are two types of matter: pure substances and mixtures. Pure substances contain only one single type of matter. We'll talk more about this in a little while. When we have two or more types of pure substances intermingled with each other, we call that a mixture. Homogeneous mixtures, or solutions, are one type of mixture. Homogeneous mixtures have an identical composition throughout. In other words, if you take a sample of a homogeneous mixture, that sample should consist of exactly the same material and look exactly the same, no matter where in the mixture you take the sample from. An example of this is when you dissolve sugar in water. If properly dissolved, the sugar water is the same throughout. In contrast, heterogeneous mixtures do not have an identical composition throughout. If you take a sample of a heterogeneous mixture, it could easily look very different depending on where in the mixture you pulled that sample from. Ice water is a good example of this. If you take a large spoon and scoop out some ice water, you may end up with a spoonful of water, or you could have a spoonful of water with some ice cubes in it. This means that your mixture is not the same throughout. As we're talking about matter, it's important to note that all matter is made up of the 118 known elements. 90 of those elements are natural, and the other 28 are man-made. The elements have names, but we often abbreviate those names into 1- or 2-letter chemical symbols. Elements are the basic building blocks of all matter. Back in 400 BC, 2 Greek philosophers had very different ideas about this. Democritus thought that you could cut a substance in half only so many times until you were left with a single particle that could no longer be divided. Based on his own observations, Aristotle thought that matter was continuous and not made up of individual particles. Democritus was actually more correct than Aristotle, which is pretty good for not having any scientific instruments to study this like we do now. But Aristotle's theory was more widely accepted, as it made sense to the people of the time. Today, we credit Democritus with being the first to come up with the idea of an atom, the smallest possible piece of an element. Elements are a type of pure substance. A pure substance that only consists of atoms of one element are considered elemental substances. Compounds, on the other hand, are made up of 2 or more different elements that are chemically bonded together. Compounds are also considered a pure substance because each molecule in a compound is exactly the same, so there's really only one type of matter present. Just like we represent elements with chemical symbols, we use those symbols to represent compounds with something called a chemical formula. The chemical formula indicates how many atoms of each element are in the smallest piece of a compound, which is often a molecule. Since chemistry is the study of matter and its transformations, we should probably briefly talk about the transformations as well. There are 3 types of transformations that matter can undergo. We're going to talk about physical and chemical changes for now, but later on we'll also learn about nuclear changes. After a physical transformation occurs, the substance remains the same substance as it was before the transformation started. The difference is in the physical state of the substance. The 3 states of matter, as you know, are solids, liquids, and gases. The transformation between each of those states is illustrated in this picture here. Each of those 6 transformations is a type of physical change. The physical properties of a substance characterize the substance's physical state and physical behavior. They can be observed without changing the identity of the substance. Each pure substance has its own set of unique physical properties, such as its melting point, boiling point, color, odor, density, malleability, and ductility. You can observe all of those properties without changing what the substance is. When a chemical transformation occurs, a new substance with new physical and chemical properties is formed from some starting substance or substances. We often call this a chemical reaction. We represent chemical reactions with a chemical equation. The substances that we start with are on the left and are called reactants, and the substances we end up with are on the right and are called products. We use chemical formulas in our chemical equations to represent what substances are involved in the reaction, and we use coefficients before each of those formulas to show how many particles of each of those substances are involved in the reaction. Chemical properties, unlike physical properties, can only be observed when the substance undergoes a chemical change. They describe the chemical nature of the substance, like whether it's flammable, reactive with other substances, is an acid or a base, is toxic to humans, and other properties. To fully understand how a substance might behave, it's important to know both its physical and chemical properties. The purpose of science is to explain the world around us. To do science, we follow the scientific method. It's not so much a linear progression of steps like you may have learned in elementary school, but it's a circular process that leads us to new understandings of our world. We usually start with a set of data that's collected from experiments. We take that data and make a generalization that summarizes it. This is called a scientific law. Scientific laws simply describe natural phenomena. They don't attempt to explain why they happen. They just present data from experiments in a generalized way. Scientific laws do not change because they don't need to. They're facts. Scientific theories, however, attempt to explain why a law exists. Theories are often accompanied by scientific models, which are physical pictures or mathematical expressions that help us visualize and understand a theory. Scientific models come with their own limitations, so it's important as you look at a scientific model to know what limitations it has and what it is good for or not good for. So once we've formed that theory, we use it to predict new behaviors and then test that prediction with new experiments. When we do experiments, we collect more data, we summarize that data into a law, and if the law states something different than we had before, we have to develop a new theory to explain it, and around we go. For this reason, scientific theories can be changed. If we find new data that contradicts our previous understanding of how things work, we can modify our current theories to create new and better ones. Good data depends on important factors, such as sample size. In all experiments, your sample size must be representative of the general population, or at least large enough to capture the behaviors of the general population. Take political polls, for example. If you only poll people from one town, you're not going to get a representative sample for the whole country. That said, we're pretty lucky as chemists because even with small amounts of a substance, at the particle level, we're actually dealing with an unfathomable amount of particles. Therefore, our sample size is generally not a problem. The downside of that, though, is that particles are so small we can't actually observe them in action. So we have to make inferences about what happened based on our observations. Lastly on this topic, when you're looking at someone else's scientific research, be sure to check for bias. It's always a goal for scientists to readily accept changes of their understanding of how the world works when they're presented with new and exciting data. But sometimes scientists are so inclined towards a specific answer that they look for ways to make the data fit into their own theory, rather than the other way around. Many people see science as something that is stagnant, never changing, and always 100% correct. Well, that's just not true. Science gives us the best explanation of the world based on the data we currently have. As we're presented with new data, we can form new explanations. Before we part today, I want to talk a bit about how you can use your textbook in this class. I will always encourage you to read the chapter as we go through it. Occasionally, I'll even require you to read it. Regardless of whether you're reading it because you actually want to learn and do your best in here, or because I'm telling you you have to, here are a few key tips to getting the most out of your textbook. Overall, this book largely focuses on the fundamental concepts of chemistry. Though it seems like it at times, chemistry is not just about mathematical expressions and numbers. If you focus on the illustrations in this book, you'll not only understand the concepts on a deeper level, but you're more likely to remember those concepts and be able to explain them later on. As you read each chapter, set aside 30 to 45 minutes, depending on how quick of a reader you are, to do so with absolutely no distractions. Take your time and read the chapter slowly. Have a paper and pencil on hand to jot down notes, draw sketches, and write down any questions you come up with so you can bring them to class. Since this is a college course, I'm not going to require you to take notes like we did in Chem 1. I strongly encourage that you do, but I'm not going to grade your notes. As you read through the chapter, you'll notice something called work patches. These are quick little checks for understanding that'll help you make sure you understand what you just read before you try to move on into other material. If you're having trouble with a work patch, there's a QR code and a website on the page just before Chapter 1 starts that you can go to get some hints. Make sure you stop and complete the work patch when you encounter it, and don't move on in the chapter until you have it figured out. There are also practice problems laced throughout the chapter. There's usually an example problem that shows you how to do it, and then gives you a couple to try on your own. I strongly recommend you do these as well. The ones that have blue numbers even have the answers in the back of the book so you can check your work. If you want to delve a little deeper into some of the more interesting stuff, feel free to read the One More Thing section at the end of each chapter. Lastly, right before the chapter questions at the end of the chapter is a list of learning outcomes. Read through that list and make sure you can do all of those things. If you're struggling with any of those learning outcomes, reread the pages listed. If you're still having trouble, be sure to ask me for help in class. Well, that's it for today, folks. As always, please let me know if you have any questions.